Okay, so let's jump in with some new stuff. Today is, we're going to cover lesson 25 and we're going to start lesson 26. And I'll just point out they're highlighted over here. Quadratic models, that means word problems. So we're going to do some word problems where quadratic equation is the thing we'll have to solve at the end. And then we'll start our second day on graphing parabolas and also do some more word problems, different kind of applications for that second day. And also coming up on Thursday, 2 days from today, is quest number 4. You can see quest number 4 is on lessons 19 to 24, but today we are doing 25. So none of the new stuff for today is on the quest on Thursday. Okay. And again, real good source of practice problems for that quest is that separate practice problems packet, right? Separate handout, 19 through 24. Any questions on the calendar? Okay, and then it's going to be here before we know it, but May 16th, I'm pretty sure that's 3 weeks from today for our final exam. On Tuesday during final exam week, 3 weeks from today. Okay, so here we are on page 204. In this lesson, we tackle some word problems that lead to quadratic equations. So number 1, a farmer has a rectangular garden plot surrounded by 200 feet of fence. Find the length and width of the garden if its area is 2,400 square feet. 2,400 square feet. So let's give this a shot. The whole solution is written out. We're just going to write down a few highlights for the solution. So we draw a picture. And we've got 2 L's for lengths and 2 W's for widths. And then we're going to have to write down some equations. So when we say the plot is surrounded by 200 feet of fencing, what geometry word are we talking about? It's not area, 204. When we say we're surrounded with 200 feet of fence, that's a perimeter, right? We're not talking about how much space is inside the rectangle. We're talking about how much fence we use. So that's a perimeter. And we know that the perimeter is just adding up the 4 sides. So that's L plus W plus W, or 2L plus 2W, yeah? And we are told that that is 200. So there's one equation right there. Add up all 4 sides, make it equal 200. And then separately, we are told that the area is 2,400. L times W, right? Length times width is the area of a rectangle. So for sure, that is L times W, and we are given it is 2,400. Okay, so we've got 2 equations, there and there. And we're going to solve these 2 equations at the same time, and we're going to find a single L and a single W that work, that make both equations true simultaneously. Now, we have a lot of experience this semester with solving 2 equations and 2 unknowns, but they look different. At least one of the equations here looks different from all the ones that we solved earlier this semester. So let me write down something like this. 3x minus, you don't need to write this. But we solved equations like that a bunch, didn't we? It would be like a month or so ago. And we used either the substitution method, where we would solve one equation for one letter and substitute into the other, or we solve the with this elimination method or the add subtract method. Maybe you multiply this equation by 2, and when you do that, you have a 2y here, which when you add to this negative 2y, the y's will cancel. So we had 2 different techniques for solving equations like that. Okay, this whole add subtract method is really only good if you have equations that look like this, where it's like additions and subtractions. And this L times W is no good. There is nothing I can do to add or subtract these 2 equations and make L or W disappear. But the substitution method is more general, more widely used. And we're going to use the substitution method here. So what that means is that we are either going to solve the first equation for L and substitute into the second equation, or solve the first equation for W and substitute in, or solve the second equation for L and substitute up here, or solve the second equation for W and substitute up here. All 4 of them are perfectly valid, but I'm going to try to encourage you to go away from 2 of the things that I just said. If you solve this equation for L, what do you have to do to both sides? This W, how does it get to the other side? Is it subtract or is it divide? It's divide. You have to divide by W, right? divided by W. Totally fine, but you just introduced fractions into the rest of the problem. It's legal, but I don't know. If I can avoid fractions, I do. If you solve this one for W, to move that L, you still have to divide. And you have again introduced fractions. Don't start there. Start up here, because there's no multiplication. This is an addition, and we can get rid of that guy without dividing. Okay, I'm going to write some stuff. Don't write this yet. We're going to come up with a better way. For example, suppose that I said I want to get L by itself. That means first I move the 2W over by doing what? Subtracting. Don't write this. Yes, subtract 2W from both sides. And then to get L by itself, what do we do? Divide by 2. And again, we have managed to bring fractions into this problem, right? But there's one way we can do this which totally avoids bringing fractions into the problem, and that's the way I think we should do it. So let's get rid of all this and come back to here. And I'm going to say this. If the whole perimeter is 200, then how much is half of the perimeter? 100. Would you guys agree that if you take a single L and add it to a single W, you are going to get 100, half of the perimeter? L plus W instead of 2 L's plus 2 W's, yes? And by doing that, we have gotten rid of this 2, which means we are not going to have to divide it all. Write that. This is how we're going to solve it. Okay, so we can substitute. We'll first solve for L. We could just as well solve for W, but we'll solve for L. So move the W over by doing what? Subtracting. So 100 minus W. And then instead of this L right here, what can we put? 100 minus W, right? Because that is equal to L. So we are substituting into that green equation, instead of L, 100 minus W. Gotta have parentheses there. So that's the key. The rest of this problem is going to be pretty routine. But this is really the new part. I need you guys to see this equation here follows directly from the two that we have written up above. It's just a straight substitution. You are replacing L with something that is equal to L. The benefit of writing the bottom equation in this way is that there's only one variable in it, just a single W. Well, W appears a couple of times, but it's just W's and not W's and L's. You see it? Okay, and then solving this equation for W is, like I said, fairly routine. I'm actually just going to point here instead of writing out the rest of it. Where is it? If we distribute that W in here, we get 100W minus W squared. Fair? In this equation, the 2400 was on the left instead of the right, but it's the same. What number do we really like on one side when we have quadratic equations? We really like 0. So let's make a 0 on one side. Where is it? Oh, it actually doesn't have it written up here. But you could make a 0 on one side. 100W minus W squared minus 2400 equals 0. By subtracting 2400 from both sides. And then you can solve that equation using one of two different techniques. They're both going to work. You could either use the box, it will factor, or you could use the quadratic formula. You'll get the same answer either way. When you solve this equation, you will get W equals 40 and W equals 60. What do we still need to find for each of those W's? What's that? Well, so yeah, you might use the quadratic formula, which means you need to find the A, B, and C. But after you've done that and you get your answers, I'm telling you the two answers are the width is 40 or the width is 60. What do we still not know about the rectangle? It's the length. It's tempting to say, oh, it's a 40 width and a 60 length, but that's not what it is. I mean, there's no L's in this equation we just solved. We are going to find two different W's, and they are both widths. Neither of those is a length. So you still need to find the corresponding lengths, and we have an easy equation that you can use to do that. It is right here. If you know the width, you plop it into that equation, and it spits out the length. So if the width was 40, then you put a 40 right there, and what do you get for the length? 60. And if instead the width was 60, you plop a 60 right there for W, and what do you get for the length? It's 40. So it turns out there's two rectangles, but they're basically the same rectangle. It's either a 40 by a 60 or a 60 by a 40, but it's still the same rectangle. Okay, any questions on that? Okay, next page. We're going to do some physics here together. So number 2 says this problem involves a baseball being thrown. Here's the setup. The formula for the height of a baseball thrown into the air is h equals negative 16t squared plus 64t plus 4, where h is the baseball's height in feet, and t is the time in seconds since it was thrown. Okay, so just imagine a baseball going up in the air and coming back down, and this formula tells you exactly how high it is at every moment in time. So like when this person throws the baseball, you got a stopwatch in your hand, you start that stopwatch, and plugging different times into that equation will tell you exactly how high this baseball is off the ground at that moment in time. Let's see if we can start by filling in this table. It says use that equation to complete the table of values. So I'm giving you 5 different t's and asking you to find h. So we could probably do a bunch of this without a calculator, but let's use a calculator to make it a little bit quicker. Although the first one we should definitely do without a calculator. When you plug t equals 0 here and here, what do you get for the whole thing? There's just 4, right? Everything blanks out except for that 4. So when time is 0, the height is 4. That means the moment we hit that stopwatch, the baseball's 4 feet off the ground. So the person's throwing it from a height of 4 feet off the ground. And then we plug in t equals 1, there and there. 1 squared is 1, so that's really just the negative 16 times 1, which I won't put, plus the 64 plus the 4. So 52, is that okay? Okay, now we're going to do t equals 2. So that formula says t squared. How much is t squared? When t is 2, it's 4, right? Plus 64 times t. How much is t in this case? It's 2. And then always plus 4. Everybody see what we're doing here with this formula? I got 68 there. Okay, we're going to take the next 60 seconds in your groups. Fill in the other 2 numbers. You can do it by hand, or you can use the calculator. If you need to borrow a calculator, come on up and grab one. If you had any trouble getting these things on the calculator, just call me over during the activity. But it's important to me that we can use the calculator to get the right numbers here. Okay, next up, it says on the grid at right, graph the height of the baseball versus time by plotting the points from your table above. So what we are saying here is that the horizontal axis is t, which is time, and the vertical axis is h, which is height. So you're going to plot those 5 points very carefully in that grid. And once you've plotted your 5 points, you're going to connect those points with a smooth curve. Because of that t squared in the equation, we know this is going to be a parabola. Surprised or not surprised that this parabola opens down? Yeah, it is a height and a time thing. And we know the ball goes up and then comes down, so that's not a surprise. What in the equation would have told us that it opens down is negative 16, right? Negative in front of the t squared. Okay, so no surprise there. Let's fill in part C. Coordinates of the highest point, what are they on this parabola? I know, I think I missed a couple of them. What are the coordinates of the highest point? 2 and 68, right? All right, now if you're really on the ball, you might be wanting to call me out and say, hey, how do we really know that 268 is the highest point? It's just the highest point in the table, but isn't it possible that if you go to 2.1, it's a little bit higher? Right? So we really don't know that 268 is the highest point. It's the highest point we plotted, but that doesn't make it the highest point any place. But in this case, I actually think it is the highest point. As soon as you have symmetric points, the highest point has got to be smack dab in the middle, right? We did it before with the x-intercepts to find the vertex. We would just say, oh, if you know the x-intercepts, then you just average them, and that tells you where the vertex is. So we got lucky here because this was particularly chosen, so the vertex would be an integer. Okay, the baseball reaches its maximum height at how many seconds? Is 2, that's what the 2 is, so fill in the 2. And what is the maximum height of the baseball? Is 68 feet. So we've got two different numbers here, 2 seconds, 68 feet, right? This is just us interpreting what those numbers mean. Okay, so it turns out that this really wacky formula that I came up with here is part of a more general thing that happens with any falling object, and not just here on Earth, but for example, on the moon, objects would still go up and they would come down. It would take longer, right? Because gravity is not as strong on the moon as it is here. But there is a general formula that governs all motion, falling objects, and it is right here. It says that h is equal to 1/2 times g is gravity, times t squared, plus v sub 0. That v sub 0 looks like two things. It's really just one thing, and it is the initial velocity. The v stands for velocity. The 0 is like the 0 on the stopwatch right when this ball is being thrown. You got it? V sub 0 is supposed to represent the start of something, the start of the velocity. And h sub 0, again, that is a starting number. It is the starting height of the object, okay? And so in our example, how much was h sub 0 for the one we just did up above? It was 4. And in fact, we found by plugging in t equals 0 into our table that yes, the starting height was 4 feet off the ground. What we didn't know up above was that the initial velocity of that particular baseball was, what's the number touching t? What is it? 64. I'll put some units up here for our velocity. The ball was initially thrown with a velocity of 64 feet per second. Okay, and then here is a fact on Earth that the gravity is negative 32. I'm going to put units here. You don't need to ever worry about the units, but I will put them. This is just a constant that is specific to our planet Earth, that the acceleration due to gravity is negative 32 feet per second squared, or said another way, negative 32 feet per second. On the moon, it's a different number. And so do you guys see, if you do half of RG, what do you get? What's half of RG? Half of this number, G, is negative 16. Do you remember, you saw the negative 16 in front of the t squared? That was no coincidence. Everything on Earth, every falling object here on Earth is going to have a negative 16 in front of that t squared. Again, on the moon, it would be different. Okay, so let's see if we can use that formula to answer one simple question here. In number 4, it says a tennis ball is thrown into the air with an initial velocity of 25 feet per second from a height of 8 feet. We want to write a formula that gives the height of the tennis ball at time t. Let's give it a shot. Okay, h equals. All right, I'm just copying this formula right here, but I'm changing as many letters to numbers as I can. So it is always 1/2 gt squared. G on Earth is a constant. What is it? Negative 32. Just put it as negative 32 every time we're doing a problem here on Earth. T squared gets copied. Plus. Next symbol I see, V sub 0. That is initial velocity. What is it for this tennis ball? 25. Just change it to 25 times, and then you copy the T. Plus, H0 stands for initial height. What is it for the tennis ball? 8 feet plus 8. That's it. That's the formula. There's only one thing we can do to clean this up a tiny bit. Half of negative 32, again, becomes the negative 16 we saw for that baseball problem. Questions on creating the formula? Okay, so two kinds of problems you're going to tackle in the activity right now. One of them is like that farmer problem where you're going to write two equations with two variables, like a length-width equation and another length-width equation, and then you're going to do substitution in order to solve. And then this kind of falling body problem, and you'll see a couple of different kinds of questions I can ask you about those. All right, so activity is on the next page. Go ahead and jump in, and I will walk around.